So this example says we have 16.67 mole per second of pure ethanol enters a steady state boiler as liquid. So the inlet here is liquid at 101.3 kilopascal, 298 Kelvin, and leaves this boiler as a vapor at given pressure at 373 Kelvin. As shown in this figure, the normal boiling point of ethanol is this one. So this is the normal boiling point we have of this ethanol. And we need to find what is the amount of heat. What is Q we have in this example? So this is the first example. We have change in the phases happening inside the process. We have inlet coming inside. We are heating this liquid, okay, and then we have vaporization will happening inside. So how can we solve this problem, or how can we apply energy balance in this problem here? So the same thing, we will need to apply energy balance. So we have accumulation equal in minus out plus work of expansion contraction plus shaft work plus Q. The general form of the energy balance. Always start with this thing. Then see what terms that will be cancelled. We have steady state boiler, so accumulation is 0. We have no expansion contraction. We don't have any changes in the total volume. We don't have any rotating or moving part, so we have no shaft work. So basically this equation tells you Q that you need to find. This will be whatever we have in the out minus whatever we have in the inlet. And again, we have the molar flow rate. This is given. So this will be N dot out times. Here the first term, we will use enthalpy or internal energy. This system is open or closed? Is open. We have inlet, we have outlet. So we're going to use enthalpy or internal energy? Any idea? Enthalpy, okay. So this will be molar enthalpy of the outs plus kinetic energy of the outs plus G H out minus inlet molar flow rate, molar enthalpy of the inlets plus inlet velocity plus G inlet height. Again, in this example, he didn't mention anything about height or level variation between inlet or outlet, so potential energy will be cancelled. He didn't mention any changes in the pipe diameter of the inlet and the pipe diameter of the outlet, similar to the first example we discussed in the previous lecture. So the kinetic energy also will be cancelled. So based on this thing, then Q, and this is what we need to find, will equal the molar flow rate is also the same. So N dot in, N dot out, the same. So I can take this as a common factor. So this will be inlet times delta H. So this will be our Q. So I need to find Q. So I need to know what is my molar flow rate and what is the change in the molar enthalpy. The molar flow rate, this one is given. So this one is easy. I have 16.67 mole per second. So what I need is to find delta H. Clear? Okay, so when I tried to find delta U in previous examples, I said du is CV dt. So what will be dH? Yes, I hear it. What is dH? If du is CV dt, so dH is Cp dt. So the heat capacity at constant pressure dt. Okay. But, and this is very important to note, in all the previous examples, we have only one phase. So this is very important, just note this one. So if we have single phase, then we can directly integrate the equation to find the change we have in the enthalpy. If we have single phase, no phase change, and you need to find delta U or you need to find delta H, so du is CV dt integrated, dH Cp dt also integrated, and that's it. This will be straightforward, similar to what we did in the previous examples. But here in this example, we have phase change. Because inlet was liquid and the outlet I have in this example is vapor. And note that the heat capacity, or even CV by the way, for liquid doesn't equal Cp or Cv for vapor. And this is the key here. Since you have one phase, so you have one Cp, or you have one Cv, so you can integrate. But here in this example, we have two phases. So if you integrate this equation, the question, which Cp you will use? Will you use Cp for ethanol liquid or Cp for ethanol vapor? Because Cp for ethanol liquid is different from Cp for ethanol vapor. You have in the appendix, appendix D, you have appendix D1, it gives you value of Cp for vapor. D2 gives you Cp for liquid. So this is totally different. So this is why we cannot integrate this equation. But instead what we can do here, we can think of using hypothetical paths. And do you have mass and energy balance course, right? You have it this semester or you take before? Any one of you finished mass and energy balance? Okay. So do you hear about this hypothetical path? Yes. Yeah. Okay. So at least you hear about it. So what is happening here? So let's start. That's it. This is my initial state. I have liquid. This liquid at 100.3 kilopascal, 298 Kelvin. So this is liquid. If you start heating this liquid, so you start adding sensible heat. If you remember the difference between sensible and latent heat, so you start adding sensible heat, what will happen to the temperature of this liquid? It's increase. And this liquid temperature will increase until it reaches the normal the normal temperature or saturation temperature or boiling point, which is given in this example, which is 351. So if you keep heating this liquid, it will move from liquid at 101 kilopascal, 298 Kelvin, to liquid at 100.3 kilopascal and 351.55 Kelvin. And again, this temperature here we have, this is the boiling point of this component. Okay, and this was given in the example, by the way. There's no need to bother yourself with it. Then what we have, if you add any heat to this compound, to this liquid at this boiling point, what will happen? So its temperature will increase, or the phase will start to change. Then we have phase change will happen. Now this is saturated liquid. So any amount of heat added to this saturated liquid, it will be converted from saturated liquid to what? To saturated vapor. You remember these diagrams? Okay, so adding this or any heat here. So this one will be vapor at the same temperature and the same pressure. 351.55 Kelvin, and again this temperature here we have let's do it this way. So this temperature, this is the boiling point. Of ethanol at 101.3 kilopascal. Then if you add any heat to this one, so now you will increase its temperature to your final state. So whatever we have, I need to find delta H here inside the boiler. So instead of having the change in one step, I make the change on 3 steps. I have liquid, add heat to this liquid, so I increase the temperature of this liquid until it becomes saturated liquid, until it reaches the boiling point. Then I add heat to this saturated liquid at the boiling point, so the liquid will be converted to vapor at the same temperature, at the same pressure, which is latent heat. Then I continue adding heat to end up or to reach the superheated steam or the superheated conditions, which is whatever final temperature I have here. So in order to calculate delta H for the whole process, so I divide it into 3 steps. So I need to find the change in the enthalpy for the first step, I call it delta H1. I need to find the enthalpy change for the step 2. I need to find the enthalpy change for step 3. And here the idea, the whole idea of this hypothetical path is this. Delta H for the whole process is the enthalpy change for the first path plus the enthalpy change for the second path plus enthalpy change for the third path. So this is the key here. Is it clear? So delta H1, this is enthalpy change for liquids. For the first path, initially we started with liquid at 298 and we end up with liquid at the boiling point. The third path, we have vapor, saturated vapor, and it will be superheated vapor. The path number 2, this is a phase change process. This is latent heat of vaporization. Clear? Any questions? Okay, so how we can find this path is here. So let's start with the easiest one, which is delta H2. Delta H2, this is the enthalpy change due to phase transition from liquid to vapor. Okay, and this one you can find directly the value of this one. You can go to appendix C1 and you can find this value. So if you go to appendix C1, look for your substance, which is ethanol. So for ethanol, you can find delta H vaporization, which is delta H2 in this example here. This one will be 36560 kilojoule per mole. Okay. Clear? Then we need to find delta H1. Delta H1, this is enthalpy change due to increasing the temperature of liquid ethanol from the initial temperature, which is 298 Kelvin, to the boiling point. And how we can find this one? So this one we will write the equation. So dH1 is Cp dt. So by integration, so we'll have delta H1 is the integration of Cp dt, but not here. This Cp is for liquid ethanol. And this in appendix D2. So in appendix D2, you will find the value of, or the equation for Cp for liquid ethanol. So get this equation, substitute Cp from this appendix into this equation, and then we can say by integration then you can find that delta H1, this one is 6253 joule per mole. That's divided by 1006.253 kilojoule per mole. Is it clear? Okay. Delta H3, so this one is enthalpy change due to increasing the temperature of ethanol, but this time ethanol vapor, from the boiling point to final temperature, which is in this example 373 Kelvin. So this one is for vapor, but the same equation will be used. So dH3, this one will be Cp dt by integration. So we have delta H3, this one will be the integration of Cp dt, and the integration will be from T1 to T2. So this one T1 to T2 here. And again, this Cp is for ethanol vapor. And this you can find it in appendix D1. So go to appendix D1 for ethanol vapor, find the value of Cp for ethanol vapor. Get this value, put in the equation, and then you can integrate. And then by integration, then you can see okay, so you can see by integration then delta H3, this one will be 1621 joule per mole. If we divide by 1000, it will be 1.621 kilojoule per mole. Is it clear? So now if we recall the energy balance equation, we have the energy balance equation Q is N dot delta H. So let's get back here, recall the energy balance equation. Q, this is what we need to find, is N dot delta H. So this one will be N dot 16.67. Delta H is delta H1 plus delta H2 plus delta H3 all these should be in kilojoule per mole or joule per mole, but they must be the same. So let's do it in kilojoule per mole. So this will be delta H1 is 6.253 plus delta H2 is 36. 560 plus 1.621. So if you just find whatever we have here in this equation, so this one will be 740.7 kilojoule per second, and kilojoule per second is equivalent to kilowatts. So this is Q. This is the final value of Q I need to find. Is it clear? Any questions? Joule or kilojoule? Let me... 36,560. This is joule? Okay. Maybe I write it wrong. Okay. So let's say if this is joule, so this will be, yeah, this just will be point. Let me do it. 6.560. So now, okay. Now the last part in this chapter, we have this table. So this table, they applied the energy balance equation for different chemical process, and this is the summary of the equation. So let's say if you are applying, or if you have solving example on valve, so you should expect that this will be the final form of the energy balance equation for the valve, that the inlet enthalpy equal the outlet enthalpy. If you have nozzle, for example, nozzle was the first example we solved. So after you write the whole energy balance equation, try to cancel whatever term is in this equation, and you will end up with this equation here. So this table, just you can use it or check this table when you are solving any example. If you have any example on heat exchanger and you have the whole energy balance equation, after cancelling the terms that its value is not significant or can be neglected, this will be the final energy balance equation form. So for these like 5 chemical process, the energy balance equation or the final form of the energy balance equation is there, so you can use this equation directly. But if we have boiler, for example, then it's not one of these, so we will start with the whole energy balance equation, cancel any terms we have.